Let's begin this reading by defining a probability distribution, which basically lists the probabilities of all possible outcomes in a random variable. For example, when you toss a coin, this is the probability distribution. There are two possible outcomes, and the probability of each is 0.5. If a random variable is discrete, it means that you can count the number of possible outcomes. Examples of discrete variables would be stock prices, or the number of eggs that a hen lays in a day. There's a finite number of possibilities for each one. Compare that to a continuous random variable, which has an infinite number of possible outcomes. For instance, the inches of rain in a month. The actual amount might be 1 or 2 centimeters, but could also be half a centimeter, a tenth of a centimeter, 1.978 centimeters. Essentially, an infinite number of decimals. That's why continuous random variables are expressed in ranges, such as the probability of getting between 1 and 2 inches of rain. This is because the probability of an exact value, such as 2 inches, is considered 0. You should also be familiar with the discrete uniform distribution. Take a look at this table. It shows the probabilities of each possible outcome when you roll a dice. So you can end up rolling any one of these 6 discrete variables. If we wanted to graph this distribution, here is what it would look like. Notice that these are called uniform variables because they all have the same probability of occurring. Now, let's talk about cumulative distribution functions. Using the same table as before, let's come up with the values for the cumulative distribution. This is the probability of rolling a 1. Next, we need to add the probabilities of rolling a 1 or a 2. Next is the probability of rolling a 3 or less, and so on. So this is what the cumulative graph would look like. Notice that the last column has a value of 1, because it adds up the probabilities of rolling a 6 or less. Now try answering this question. It is asking for the probabilities of rolling a 3, 4, or 5. An alternative way would be to rewrite it as f5 minus f2. By expanding these two terms and subtracting, you can confirm that the answer is 3/6, regardless of what method you use. Let's try another question. Be very careful with the signs. Here it is only asking for the probability of rolling a 4 or a 5, so we can rewrite it as f5 minus f3. By expanding these terms and subtracting, we can confirm that the answer is 2/6, regardless of the method used. Now, let's move on to the continuous uniform distribution. This type of distribution is defined over a range with lower limit a and upper limit b. So take a look at the following example. Here we have the probability distribution for the inches of rain in a day. We can get anywhere from 2 to 5 inches per day. Notice that the probability of getting less than 2 or more than 5 inches is 0. And the total area of the orange rectangle is equal to 1. To find the probability that we get between 3 and 4 inches of rain, use the continuous uniform distribution formula. So simply plug in the values and you should get 1/3, or 33.3%. Our next topic is the Bernoulli trial. A Bernoulli trial is like a mini-experiment that only has 2 outcomes, a success and a failure. For example, flipping heads. These are the probabilities of success and failure. That leads us into binomial random variables. If we repeat a Bernoulli trial many times, binomial random variables tell you what is the probability of x successes in n trials. For example, what would be the probability of successfully flipping heads 3 times in 10 coin flips? Well, the probability of success in a single trial is 50%. And we want the probability of 3 successes in 10 trials. All you have to do is just plug in these values into the binomial formula. Remember to use the factorial button in the calculator to save time. Now pause the video if you need to, before checking your work. Here is the calculation, which should give you a probability of 11.72%. You should also know the formulas for expected value and variance of a binomial random variable, which compared to the previous formula are relatively simple. Here are the calculations and solutions for the expected value and the variance of this binomial random variable. Now, let's talk about the normal distribution. Here's what it looks like. Its kurtosis is 3, and it's symmetrical around the mean, so its skewness is 0. Notice how you have some outliers in the tails, but most data points are clustered around the mean. There are a couple of things that you should memorize when it comes to normal distributions. The first is that 68% of observations fall within one standard deviation of the mean. 95% of observations fall within 2 standard deviations of the mean. And 99% of observations fall within 3 standard deviations of the mean. Let's take a quick detour and go over some key definitions before we continue. You should know that a univariate distribution describes a single random variable, while a multivariate distribution describes the probabilities for a group of related variables. So an example would be a portfolio made up of n stocks. Its distribution would be defined by n means and n variances, but how many pairwise correlations? Well, let's say there are 5 stocks in the portfolio. So you have the correlation between stocks 1 and 2, between 1 and 3, 2 and 3, and so on. You could go on for a while, but the easy way to do it is with this formula. So according to the formula, there are 10 pairwise correlations if you are analyzing a group of 5 variables. For this next learning outcome, you should be able to explain what a confidence interval is. For a normal distribution, 90% of the data falls within 1.65 standard deviations from the mean. So 90% would be the confidence interval. We will see why later on, but first let's look at a practical example. Imagine you have a class of students and their grades follow a normal distribution. The class has an average test grade of 83 and a standard deviation of 2. As we mentioned before, to create a 90% confidence interval, we need to be 1.65 standard deviations away from the mean. We know the mean equals 83, and we also know that 1 standard deviation is equal to 2 points, so 1.65 standard deviations should be equal to 3.3 points. Now we can include that on our graph. This means that if you move 3.3 units away from the mean, 90% of the observations will fall within that interval. So let's label that interval on the graph. In other words, 90% of the students in the class received a grade between 79.7 and 86.3. You should memorize the most common confidence intervals for a normal distribution, and remember that if the distribution is not normal, then these intervals do not apply. So let's visualize each of these confidence intervals. 90% of the observations fall within 1.65 standard deviations of the mean. 95% of the data falls within 1.96 standard deviations from the mean, and 99% falls within 2.58 standard deviations of the mean. So we covered the normal distribution. Now what is the standard normal distribution? It is simply a normal distribution that has been standardized so that its mean equals 0 and its standard deviation equals 1. But why is this so important? Well, because whenever you see this type of distribution, you can use something called the z-table, which lets you find the area under the curve for any given range. Don't worry if you're not sure what that means, because we will review it in a moment. Here is what part of the z-table looks like. To use the z-table, you'll need a z-value, which is the number of standard deviations that a given observation is from the mean. The numbers in the middle of the table are the probabilities to the left of a given z-value. This is much easier to understand with an example, so let's put everything together. Remember the confidence intervals we just mentioned. Let's consider this first one. How can we prove that 90% of the data in a normal distribution falls within 1.65 standard deviations of the mean? Well, that's what the z-table is for. This range includes 90% of the data, so the remaining 10% is split between the symmetrical tails. And remember that the z-table gives the probabilities to the left of a given z-value. So in theory, the z-table should confirm that the probability to the left of -1.65 is equal to 5%. Let's see if that's true. Here is the closest probability to 5%. And if we look at the corresponding z-value, we can confirm that a z-value of -1.65 has a left probability of 5%. So let's recap. The degree of confidence was 90%. The area remaining in the tails was 10%, which is also known as alpha, and it is divided equally between the two tails. We need the z-value with a 5% probability in its left tail, which is also known as a critical value, and can be written like this. Looking at the z-table, the critical value equals -1.65. Since the tails are symmetrical, the upper value is also 1.65. But if you wanted to find it using the z-table, just look for the critical value with a 95% probability to its left. These three confidence intervals are pretty common, so we recommend that you memorize them to save time. Now, let's apply this concept to an actual practice problem. Assume that the average grade in your class is a 70. The class standard deviation is 4, and you want to know what percentage of students got a grade below 65. Well, the z-table will give us the percentage under the curve, but remember that the z-table only works for standard normal distributions. So first we'll need to standardize this distribution before we are able to use the z-table. You can standardize the distribution by using the following formula. In this case, the z-value is equal to -1.25, so this means that a grade of 65 is 1.25 standard deviations below the mean. Now that we calculated the z-value, we can actually find the probability using the z-table. So for a z-value of -1.25, the probability to the left of it is equal to 10.56%, which is the percentage of students that received a grade below 65. Now, let's review a common mistake. What happens if the given z-table does not have negative values? What you can do is use the positive z-value of 1.25. Here it is on the z-table. However, the table gives us the probability to the left of the z-value, and that's not what we want. We need this probability right here. Fortunately, the normal distribution is symmetrical, and the total probability is 1. So 1 minus 0.894 gives us the value in this upper tail, which is the same as the negative tail we were solving for. According to Roy's safety-first criterion, the optimal portfolio is the one with the lowest probability of falling below a minimum acceptable level. This is the safety-first ratio. It is the expected return above a given threshold divided by the standard deviation. If you are comparing many portfolios, the one with the highest ratio is better because it minimizes the risk of falling short. You should already be familiar with the normal distribution. So now, let's discuss the log-normal distribution, which is defined by the mean and variance of the normal distribution. You should remember the following relationship. If the natural log of a random variable y is normally distributed, then y follows a log-normal distribution. As you can see, the log-normal distribution is positively skewed, and it's bounded by 0 on the left, which is great for modeling asset prices because a stock price cannot be negative. Moving on to continuously compounded returns. Let's say a stock grows from $90 to $97 with continuous compounding. What is the continuously compounded rate of return? This learning outcome is not as tricky as it seems if you remember the following relationships. A stock's final price divided by its initial price is the same as 1 plus the holding period return, which is the same as e raised to the continuously compounded rate. So if you need to solve for the continuously compounded rate, you can just take the natural log of this term. If you're wondering why, remember this rule of logs. By taking the natural log, we have isolated the compounded rate, but we must keep the equation in balance. So take the natural log of the other two terms so that everything is still equivalent. Going back to the original question, you were given the final price and the initial price, so let's take the natural log to find the continuously compounded rate of return. You should get a return of 7.49%. This next learning outcome covers the t-distribution, which looks like this. It has a lower peak and fatter tails in comparison to the normal distribution, and it is defined by a parameter called the degrees of freedom, which is equal to n-1. As the degrees of freedom increase, the t-distribution changes, and it becomes more similar to the normal distribution. When you are analyzing a t-distribution, you can use a t-table to find its critical values. For example, let's find the t-values for a 90% confidence interval. The t-table focuses on the probabilities in the right or upper tail of a given value. The upper tail probability is located in the top row. The degrees of freedom are found on the first column. And these middle values here are your critical values. So let's actually apply it. Since the confidence interval is 90%, the level of significance, which is the probability that remains in the tails, is 10%, which is split between the two tails. The upper tail probability is 5%, and assuming that the sample size is 30, the degrees of freedom must be 29. Using the t-table, we can see that an upper tail probability of 5% and 29 degrees of freedom give you the critical values of plus and minus 1.699 for a 90% confidence interval. Here are the most common critical values for the t-table, which will be useful in upcoming readings. You'll notice that the critical values are not the same as the z-tables, and this is because the t-distribution is flatter than the standard normal distribution. Let's review two more distributions that are mentioned in this reading. The chi-square distribution is asymmetrical, has no negative values, and is defined by its degrees of freedom, which are equal to n-1. As the degrees of freedom increase, the distribution becomes more similar to a bell curve. The F distribution is also asymmetrical and is defined by two parameters called the numerator degrees of freedom and the denominator degrees of freedom. As both degrees of freedom increase, the distribution becomes more similar to a bell curve. The chi-square and F distributions are used in some types of hypothesis tests, but we'll get to that in a later reading. Now let's wrap up this section with the Monte Carlo simulation, which uses computer software to simulate a complex financial system. Its main uses include estimating risk and return in investment applications, valuing complex securities that don't have an analytic pricing formula, complementing analytical methods, or conducting a sensitivity analysis. Let's go over a very basic explanation of how the Monte Carlo simulation works. Assume that we want to figure out the correct price for this security. The first step in the Monte Carlo simulation is to figure out what are the risks or any other factors that affect the price of this stock. Then, figure out the probability distribution of each risk and input them into the model. Once that's done, the model will generate a random variable for each risk that is within the boundaries of the distribution for that risk. All of this is used to come up with a price for the security in that scenario. But we're not done. We will then repeat this whole process thousands of times and let the model come up with thousands of prices. This creates a probability distribution of all the prices predicted by the model, where we can identify the average or expected price. Some limitations of the Monte Carlo simulation are that it provides statistical estimates instead of exact results, and that it does not provide insight into cause and effect relationships. You've reached the end of the reading. Keep up the good work.
For more videos like these, go to wallstreetnotes.com and master the entire CFA curriculum by watching simple animated videos.